the one mean hypothesis test. So the one mean hypothesis test is a test we carry out of a one mean, and by mean we're talking about average, the mean average, the calculation we've already gone over. So we do this kind of test when we have a single quantitative variable we're testing that is measured in integers or decimals. So it's not a proportion. It's not a proportion. It's just a value. And it could be any value, 3, 5, 10, 100, 1,000. It depends on what the variable is. And there's just really an infinite number of things we could measure. Mercury levels on fish, height of people, number of friends a person has, speed in a bike race, right? So speed in a bike race, maybe we measure this in miles per hour. So maybe it's, I don't know, 40 miles per hour. It's probably too fast, but 40 miles per hour. Number of friends a person has is just an integer. So that maybe it's just, 5 or 7 or whatever, 11. Height of people. All of these are measured in different units, but they're all integers or decimals. So we just have expanded by using this one mean test the kind of values we can measure quantitatively and we can test, and then we'll see what we're testing against or what we're comparing against. So just for some terminology, like we usually do in notation, n is the sample size, x bar equals the mean of the sample, s equals the standard deviation of the sample, mu is the mean of the population, and I forget the name here, rho, population standard deviation. No, I don't think this is rho actually. I'll double check. But we have the population standard deviation. Also, some other terminology here. When we do the one mean test, we're going to do the theory-based approach. There's other approaches, but we're going with the theory-based approach. We're assuming a normal distribution or a normal like distribution. So, and we're assuming the central limit theory. So when we collect a sufficiently large sample of n independent observations from a population with mean mu and standard deviation, the sampling distribution of x bar will be nearly normal. Mean equals the mu. So that's just to say that as n goes up, as n reaches infinity or goes up, we're going to have a normal distribution, and then the mean is going to be whatever value is going to be mu. We're going to call it mu, and then a standard deviation by this formula here. And also some conditions for modeling using this theory-based methods, which are the same ones for the proportion. So for us to actually apply any of the methods, any of the functions we're doing here, we need to check these two basic conditions. One is independence. So are the observations independent from each other? And the best way to satisfy this condition is when we have a random sample, simple random sample. So if you want to measure cancer rates and you pick up the population, all the population that are in a bar at night, this is not independent because they are all connected via that bar going activity. And maybe something about going to the bar increases their chance of getting cancer. So that's not an independent sample. So, but if you do have a random sample, we can assume we can conclude it's the independent. And then normality. So when a sample is small, we also require that the sample observations come from a normally distributed population. We can relax this condition for larger samples because we're assuming that if the sample grows, it approaches a normal distribution. Now, this is not always the case, but often it is the case. And when these conditions are satisfied, then the sampling distribution of the mean of the sample is approximately normal with the mean the same as the population. So we're just saying that if we have a normality, we have that the data seems to be normal, then we can assume that our mean is also going to be the population mean. And how do we know if it's normal or not? Well, we will take some look at it. We can take a look at the sample, um, and we look at our n. So if the n is less than 30, that's not a good sign. But if the sample size of n is less than 30 and there are no clear outliers in the data, then we typically assume the data come from a nearly normal distribution. If n is greater or equal to 30, and there are no particularly extreme, so even more extreme outliers, then we can assume that this is a nearly, at least nearly normal distribution, and we can go ahead with the methods that we have. So we can create a histogram of the sample that we have. So if you come up with a histogram like these two, for example, do these look normal? What do you think? Well, as we usually draw out a normal distribution kind of is smoothed out like this, and it doesn't have to be smoothed out like this when we are creating our histograms, but generally should at least reflect this shape. And obviously this one does not. So this doesn't look like a normal distribution. And this kind of actually does approach one side of the normal distribution, but this outlier here seems very extreme, and the distribution doesn't seem a little bit more completed on this side as well. So I would say these don't really look normal, and these are some kind of the visual tests we want to do to see if our sample is at least approaching normality. So that's it, and next we'll continue with the t distribution.